Hey guys, hope everybody's doing okay. What we're going to do right now is continue with our vapor pressure equilibrium practice problems. Once we get through these next 4 sample problems that are a little bit more rigorous and a little bit longer to solve, then you guys will have a chance to work on some practice problems on your own, either for homework or for extra practice, and we can go over the answers to those at a little bit later time. So we're on vapor pressure question number 6, which says a 750 milliliter flask contains only water and ethanol at 79 Celsius. Total pressure is 360. So total pressure is 360. Flask contains twice as many water molecules as ethanol molecules. So what's the pressure of the water vapor? Let's figure that out first. That's question number 1. So I'll go through and show you a little bit of work wherever I can find space on here. We can go from there. So the total pressure, remember the total pressure is the combination of all of the partial pressures that make up your system. Okay, so we have 2 partial pressures here. We have a partial pressure of water and a partial pressure of ethanol, right? So it tells us more information. It says we have twice as many water molecules as ethanol. So I'm going to set ethanol equal to X, and that means water has to be 2X, right? Twice as much water as ethanol. Ethanol is X, water is 2X. Total pressure is 360. Okay, a little bit of algebra. 360 equals 3x, 2x plus x. Simplify, you get x equal to 120. Okay, 120 torr. That tells me that the pressure of water is 240. Okay, partial pressure of water is 240, because it's twice as much of it as ethanol, right? Twice as many particles, twice as much pressure. Question 2, is there any liquid in the flask? Well, now that we know what the partial pressures are of everything, we can look at our curve here and figure it out. So partial pressure of water at 79 is 240. So 300 is between 200 and 400. So we're talking like, I don't know, around here maybe. Okay. Partial pressure of ethanol at 79 Celsius is 120, okay, because X is equal to 120. So 120 is maybe here-ish. Okay, so question 2, is there any liquid in the flask? There's only liquid in the flask if we're at a saturated point, right? So remember, the saturation point is along these lines, right? These curves that are here, okay? So we're dealing with water. That was our top dot here. It's below. So the water pressure is below the saturated point for the vapor pressure. So it really could be here, like we could hold this much where I put that little X on the screen. So water is unsaturated. So there's no liquid water. It's all in the gas state because it's unsaturated. And then the ethanol, I mean, that line, that curve's here. Like we're way below that. So this is, like this point here is unsaturated as well. So both of these are unsaturated, so we have no liquid present whatsoever. So we could add a little bit more water, a little bit more, well, a lot of it more ethanol until we reach the saturation point. Okay, so is there any liquid in the flask? No, there's not. Number 3, if we slowly cool the flask, what temperature will we begin to see condensation? So this is our water point right here. Let's slowly cool it, drop the temperature, and we see we hit our saturation point right there. But with ethanol, we gotta cool it, cool it, cool it, cool it. It doesn't start to get our saturation point until here. Okay, so water right here will start to condense at around 70. Okay, around 70 Celsius. Okay, so water will happen at 70. Ethanol is not going to condense until about, what's that, 35 Celsius? All right, so if we slowly cool the flask, what temperature will we see condensation? We will begin to see it at around 70 Celsius because the water will start to condense. Okay, what liquid will it be? It'll be water because we hit that saturation point first, right? The ethanol doesn't become saturated until we are at 35 Celsius, you know, along that, like if we had, like we started here at that pressure, right? So we cool it from 79 down to 35, then we'll be able to see the saturation point occur. So that's pretty easy. Last one, what's the mass of the water in the flask? So we know for the, here we are, water's right here. It's getting cluttered. Water's right here. Okay, the pressure was 240 torr, right, or 240 millimeters of mercury. It's the same thing. So we have our pressure. We have the volume of the flask. Okay, 0.75 liters. All right. We don't have the moles of water. Okay, we have R, and we have the temperature. We're going to assume what's the mass of the water in the flask. We're going to assume it's at that 79 degrees Celsius. Okay, so we have that. Convert that to Kelvin. Okay, so we have PV equals nRT. We can, since we have the pressure, the partial pressure, we have the volume, we have the R value, we have the temperature, we can solve for moles and easily convert that into grams. Okay, so take a second and do that. Solve for PV equals nRT, solve for moles. Quickly, one step, convert that from moles into grams of water and see what we get. Okay, so if you solve for this, you should get a moles value of approximately 0.0082 moles. Remember, the temperature is at 79 Celsius. You have to add 273 to that, so you get a temperature of 352 Kelvin. You convert that 0.0082 moles of water into mass of water, and you get to 2 sig figs, you get 0.15 grams. Okay, so not a whole lot of water is in there to create that low partial pressure of 240 torr. All right, moving on. I didn't realize I had the bullet points pop up here, and I didn't do a bad job of estimating. They're right where they should be. Okay, next one. A typical fluorescent light bulb has 10 milligrams of mercury in it. A 7,500 milliliter or 7.5 liter light bulb has 4 milligrams of mercury inside. What state of mercury will exist at room temperature, or what states? Equilibrium vapor pressure of mercury at 25 Celsius, which is room temperature, 0.0017 millimeters of mercury. What mass will be gas? What mass will be liquid? So for this one, I crossed out that beginning part of it because it's just like not really relevant information. It just tells you just like a fun fact, I guess. Typical fluorescent light bulb has 10 milligrams of mercury in it. Okay, let's focus on what we actually have though. A couple ways to solve this. I want to know what states of what states of mercury will exist at room temperature in this light bulb. A couple things we can do. You can take the 4 milligrams of mercury, okay, and you could convert all of it into, like, use PV equals nRT. If you haven't picked up on that, we're using this like a billion times right now. You could do PV equals nRT. Convert your milligrams of mercury into moles, okay, and then solve for the pressure, okay, and see what the pressure would be if all of this, is converted into gas, right? The other thing you can do, and you can compare that, you compare it with 0.0017 millimeters of mercury, okay? See which one's higher or lower. You could also take your vapor pressure, okay? Take your equilibrium vapor pressure, your temperature, and your volume. Take all of that and put it in Pivner and solve for moles of mercury. Then convert moles of mercury into grams and then milligrams and compare it to 4. Okay, so you could turn all of this liquid mercury into a gas and see what the pressure is and compare it to the vapor pressure that you're allowed to have. Or you can take the vapor pressure, okay, and then convert that into moles and then milligrams and compare it to this. All right, so what mass of mercury would be needed to create this pressure in the light bulb? Doesn't really matter what way we do it. The way I have it worked out is we can figure out, we'll do the latter. We'll take our partial pressure, we'll convert that to moles and milligrams and see, we'll see how it compares to this. So let's do that. We have PV equals nRT. We want to solve for moles. So we have N equals PV over RT, right? you have your partial pressure that you're allowed to have. You have your volume, 7.5 liters. You have your R value from your AP equation sheet. Temperature, 25 Celsius, convert to Kelvin. Solve for moles, it's moles of mercury, then convert that into grams and convert that into milligrams. And we'll see what we end up with. Okay, give that a try, then we'll go from there. Okay, if you plug all this in, you have your pressure, volume, your R value of 62.36, and your temperature of 298 Kelvin. You should end up with 6.9 times 10 to the negative 7th moles of mercury. Convert that into grams using a mole conversion, and then convert that right into milligrams, and you should get 0.14 milligrams. Okay, so we would multiply by the molar mass of mercury over 1 mole, and then convert that into milligrams. So put 1 gram on the bottom, 1,000 milligrams on top, solve. So 0.14 milligrams is how much mercury you need to create this partial pressure right here. Okay, so 0.14 milligrams is in the gas state because partial pressure, vapor pressure comes from the gas state, right? So the rest of it is in the liquid state. So you have 4 milligrams minus 0.14 milligrams, and you end up with 3.86 milligrams of liquid mercury. Okay, so you have 3.86 milligrams of liquid mercury, 0.14 milligrams of mercury vapor or mercury gas. All right, that's how you work through it. If you did it the other way, you could have taken the 4 milligrams, you know what I mean, and converted that into pressure, and you would see that the 4 milligrams, if you converted that into pressure, would give you a way bigger vapor pressure than 0.0017. But you would still have to do this setup here because the question says what mass will be gas and what will be liquid. You still have to figure out, once you did that, you're like, oh my gosh, well, not all of the 4 milligrams could evaporate and create this vapor pressure. So I'm going to have to do this anyway to figure out how much will create that vapor pressure. So work smarter, not harder here, and you could get through it relatively quickly. Okay? Okay, 2 to go. Okay, for this one, it says benzene has an equilibrium vapor pressure of 269 millimeters of mercury at 50 Celsius. 175 grams of benzene is placed in a beaker or a flask at 50 Celsius. At equilibrium, there's 500 milliliters of space left, so we're at equilibrium, so it's saturated. You can see that. We have our liquid state down here, and then some gas particles in here. What mass of the benzene will be in gas form? So we know that they put 175 grams of benzene in the flask. Some of it turned into a gas, the rest remained a liquid. We need to figure out which is which. Okay, how much is each one? So we're only focusing on gas here, right? So this area is that 500 mils of space is how much gas we have. That's the volume of the gas. So again, we're doing PV equals nRT here. We have the volume. Okay, it's 500 milliliters, so that's 0.500 liters. We also have our R value, always. We have temperature, 50 Celsius, convert to Kelvin. So we got that. So now what do? I can take the vapor pressure. Okay, this 269 millimeters of mercury. That vapor pressure, I could plug in for P. And I could solve this for N. Okay, what's that tell me though? You gotta think, just label and think. This pressure is only from a gas, right? So whatever my N is when I solve for this, that is how many moles of benzene evaporated to be in the gas state to give me this pressure, okay? Common mistake every year is students using PIVNERT and then saying that's how much liquid I have, okay? PIVNERT is the ideal gas law. It only tells you information about gases, okay? So knock it out, you could do that. Solve for N, and then you have to convert that into grams, right? I gave you the molar mass of benzene right here. So once you solve for n, okay, so n equals PV over RT, convert that into grams and compare it to the 175. See what we get. Okay, if you knock this out, you solve for moles. I got 0.00668. 0.00668 moles of benzene. I convert that into grams of benzene, one-step mole conversion, moles to grams, and you end up with 0.522. 0.522 grams of benzene. This is how much benzene is in the gas state, okay? Because we used Pivnert, the ideal gas law, to figure out what it is, okay? So if 0.522 grams are in the gas state, the rest of it is in the liquid state. So you do 175.00 grams minus 0.522 grams, and that'll give you what the liquid will be. And I get 174.48 grams of liquid benzene if you do sig figs the right way. Okay? So that takes care of that one. So it's all a matter of thinking to yourself, where's my gas? Okay, what's the volume of my gas? What does the partial pressure mean, right? That partial pressure means we have a saturated solution here, right? And then when I plug this stuff into Pivnert, don't just blindly plug it in. Think about what it all means, okay? Pivnert is always about gases. Last one, number 9. A 1 gram sample of water is placed in a 10-liter flask. It gives you the equilibrium vapor pressure, 25 Celsius, 24 millimeters of mercury. How much water will evaporate and exist as a gas? Okay, very similar to the last one. You know your equilibrium vapor pressure is 24 millimeters of mercury. If I use Pivnert and I use this partial pressure, and I plug it in, and I solve for moles, that will tell me how many moles of water evaporated to be a gas to create that pressure. Okay, then you could convert moles into grams and compare it to this. This is easy. We've done a couple like this now. So take a minute and knock that out. So solve for n. N equals PV over RT, and then convert that into grams of water and see what we get. Okay, so if you solve for moles, now again, you have 25 Celsius, so that's 298 Kelvin. You have your volume right here, partial pressure and your N value. You should end up with number of moles is 0.013. 0.013 moles of water. Convert that into grams, and you end up with, where is it here? You end up with 0.23. 0.23 grams of H2O. That 0.23 grams of water is the amount you need to create this vapor pressure. Okay, so that much will exist as a gas. The rest of it will be a liquid. So how much water is left as a liquid? You have 1.00 grams minus 0.23 grams, and you end up with 0.77. 0.77 grams left in the liquid state. Okay, so A is done, B is done. Letter C, what volume flask will be needed to have all of the water evaporate? Okay, easy. You're going to use P equals nRT again, but we want to evaporate all of the water. So all of this 1 gram needs to evaporate. Okay, so what do? I want to find the pressure, it's a lie, I want to find what volume flask will be needed to have all of the water evaporate. So the bigger my flask, the more could evaporate to create that pressure, right? So I know the partial pressure, P. I know that still has to remain 24 millimeters of mercury. I just have a different size flask, right? How big of a flask do I need to get more, or really to get all of this into the gas state? Okay, so all you gotta do, convert 1 gram of water into moles and plug it into PV equals nRT. But you're going to solve that for volume. Volume equals nRT over P. Okay, that will tell you how big your flask needs to be to have all of this evaporate and to create this partial pressure. Okay, take a second and do it. Solve for V, shouldn't be too hard, and then we'll go from there. Okay, when you solve for V, you should end up with 43.0 liters. Okay, you need a 43-liter flask to have all of this evaporate into the gas state to still maintain a partial pressure of 24 millimeters of mercury at 25 Celsius or 298 Kelvin. Okay, that makes sense because the more, like if all of this evaporated in a 10-liter flask, the pressure would be humongous, right? We want to make that flask bigger to accommodate all of this evaporating. Last question, if our 1-gram sample was placed in a 60-liter flask, what will be the vapor pressure of the water? So in this case, we're definitely running out of room here. I know how many moles this is, right? So I have the moles of water there. We had to figure that out earlier. Okay, we had to figure it out right here. Okay, you should have ended up with 0.0555. 0.0555 moles of water. You needed that here to get this answer. You place that in a 60-liter flask, what's the vapor pressure going to be? So you're just using Pivner again. Okay, solve for P. P equals nRT over V. Okay, 0.0555 moles goes in for N. You have your R value, temperature, 298 Kelvin, volume, 60 liters. Okay, that will give you the pressure when all of that 1 gram, that 0.0555 moles evaporates in a 60-liter flask. So knock it out, we'll check our answer, and then we'll wrap things up. Okay, if you solve that, you should end up with 17.2 millimeters of mercury. Okay, 17.2 mmHg is the answer you'll get for this one. Using your 0.0555 moles, your R value of 62.36, your 298 Kelvin, and your 60 liters volume. Okay. You'll get the hang of these eventually. Okay, it's really doing the same thing over and over again, just manipulating Pivner to solve for what you want. And you just want to be aware of when you solve for Pivner, what are you actually solving for? What does it all mean? Okay, take some time, work on some of the practice problems, and I'll post an answer key. And if you have any questions, let me know. All right, thanks, guys.